Good afternoon, good folks. So I want to pick up today where we left off last Friday. First things first, I didn't upload your guys' video from last Friday. I'm so sorry about that. I just noticed that now as I was posting the link for this meeting. So I went in real quick and started the upload, posted the link. The link will be live as soon as the upload finishes processing, which will be a little bit, but definitely by the time we're done with this meeting, last Friday's recording will be online. So if you did miss class last Friday, that link is going up right now. And I'm sorry that took a little while to get around to posting. Last time, we got to talking a little bit about the derivative as a function. And this week I want to pick up talking a little bit more about that. So I want to talk more about section 2.8. And then this week we're going to learn how to start differentiating. We're going to learn the basic differentiation rules, namely the power rule, rules for exponential functions. And then if there's time, we will get to talk about differentiating trig functions as well, although that may end up having to wait for next week because of the time we lost to the holiday last week. I think that's all of the basic stuff started here. So let's see, I don't want to burn through this paper. I need it for AQ. I'm going to go grab some more white printer paper so I can keep things nice and organized for you guys. And then we'll begin in earnest. So I will be right back. Give me just 1 second. All right. Oh, almost. Okay, hand bones, you ready to learn some calculus, buddy? A nice healthy stack of clean, fresh paper. And we can get rolling. So switch over to the dot cam. And away we go. Yeah, Helly, I went through and approved every extension that is in there. So if you submitted an extension, it has already been approved. So here we go. Today, we're going to cover section 2.8 in earnest. Now, 2.8 is a tough section, right? This is the derivative as a function. And then maybe if there's time, an intro to section, I think it's probably 3.1 on derivatives of polynomials and exponential functions. But probably this will be mostly next time. So I want to focus today on section 2.8. We have talked about the content in section 2.8 as we've been working our way through. I've been doing my best to draw lots of pictures for you guys and try to show you how the graph of the derivative relates to the graph of the original function. I've put together some Desmos resources that I showed you last Friday, and hopefully you guys have played around with those a little bit. But understanding section 2.8 is crucial to the most important bits of Calc 1. Really understanding how the graph of the derivative is a consequence of the graph of the original function. Being able to predict what the graph of the derivative will look like given the graph of the original function. That is the main skill we want to work with here. And then of course, inferring things about the original function based on the graphs and information of the derivative. Once we have a reasonable understanding of that stuff, then we're going to move to learning how to differentiate all sorts of things so you can get the algebra expression for the derivative as a function in its own right, and then use that to learn things about the original function, like where is the original function increasing? Where does the original function have a max or a min? Those sort of things we will be getting from the derivative. So understanding this is crucial to being able to do the stuff that we're going to want to do when we get into chapter 3. Okay. Are there any other notes or comments? Of course, exam 1 is on the way. Take a quick peek at your syllabus here, right? So last week we talked about these things, and we talked about this, but we didn't get to finish this section. So we're starting week 4, that's this week, with section 2.8. So I anticipate we will get through section 3.1 and 3.2, but maybe not through 3.3. Which means that we'll probably have to push the exam back just a little bit. This is totally normal, and this is why we have extra time down here. But I don't want us to fall behind too much. So just be aware that the exam, which would normally be on the week of the 21st next week, is likely to be the week after. It's probably not going to be next week. Once we finish covering all the material that is needed for exam 1, I will release the study guide. And then the test will be exactly 1 week after that. So you have a whole week to burn on the study guide, asking questions, thinking hard about those problems before the test. If you're having problems with a homework extension, if you just submitted the extension in the last few minutes, then it wouldn't have been approved yet, but anything else should have been. Double check. Yeah, so I see I got a few more in just a few minutes, and they're all from you guys. Okay, yeah, I'll come in here and grant these real quick, no harm in that. So everything is going to get pushed automatically to 21. Oh, and then we can get started. So the basic idea that you need in order to understand the derivative as a function in its own right come on, buddy. So we want to understand the derivative as a function. This is our goal. We know that for any number a and any differentiable function f, that f primed of a can be written as one of these limits, right? Either the limit as x goes to a, f of x minus f of a over x minus a, or you could write it as the limit h goes to 0, f of a plus h minus f of a all over h. And this is one number at a time. So for every number a, there is another number f primed of a. And this pairing defines a function. The input is a, and the output is f primed of a. That function is called the derivative. Not the derivative at some point, just the derivative. That function is called the derivative. F primed of x, right? So if you treat this as a function and you feed it the input a, then the output you get is f primed of a. The notation makes sense, and that's been crafted by design. It's not a coincidence. And if you want to calculate f primed of x as a function, the easiest definition to use is this one, because here you can just swap a with x. So this is the normal definition of the derivative as a function. It's the limit as h goes to 0, f of x plus h minus f of x all over h. It's the same thing. I've just replaced the a with an x, and now I'm thinking of it as a variable. Do we understand the notation? I know function notation is one of those things that some people are a little bit squeamish about. This definition we have here, the definition we've been using for the derivative, gives us a number, right? Every time you've done one of these calculations, you've gotten out a number. And that number is the slope of the tangent line. And that's mostly what we've been working with. Now the idea is I want to think of the input here as a variable. So this limit gives me the number that is the value of the derivative at one point. But I want to start thinking of the derivative as a function. So I'd like some way to get all of those numbers together into one formula. And you've seen some homework problems which do this for you. Let me pull up one or two of these. Is this guy still alive? So where did I have you calculating f primed of a? There were a couple problems. They might have even been in the previous homework. Oh no, this is it. Yeah. So for example, let's look at number 18. This is homework 3, problem 18. You are given f of x is 2x squared minus 5x plus 2. You might have had something a little bit different. Whether sign randomizes the coefficients, that's fine. They want us to find f primed of a. So I'm going to go ahead and do that. But then I'm going to swap the a with an x. And we're going to look at the two functions as functions. The idea behind this and all the problems like this where they asked you to find f primed of a without giving you a particular number a is to get you to start thinking about the derivative as a function, to see that it depends on the number a you plug in. You plug in a different number a, you will get out a different derivative, a different number. Okay, so f primed of a. Well, I can say that's the limit as, let's use the h to 0 definition. F of a plus h minus f of a all over h. That's the same as the limit as h goes to 0. What is f of a plus h? That's 2 times a plus h squared minus 5 times a plus h plus 2. And then I have to subtract f of a. So I'm going to put these in big parens to remind myself that they're each kind of one chunk. This is f of a plus h. And then f of a is 2a squared minus 5a plus 2. And all of this goes over top of h. From here, I'll do the normal thing. I'll FOIL this out. I'll distribute this. I'll distribute my minus sign. I get lim h to 0. Instead of writing the big long fraction with the h downstairs, I'll write it as 1 over h times 2. A plus h squared is a squared plus 2ah plus h squared minus 5 times a plus h. I'll go ahead and distribute that. That's minus 5a minus 5h. And then I've got plus 2. And I'll also distribute this negative. So then I'll have minus 2a squared, distributing the negative to this piece. When I distribute this negative to this piece, it'll become a plus 5a. And when I distribute the negative to this piece, it will become a minus 2. Everybody with me so far? We foiled this into this. And the 2 stays out front. He's multiplying all of a plus h squared. So following your order of operations, we still need these parentheses here. I'm going to distribute the 2 in a second. I distributed this minus 5 across this a plus h. That gives me minus 5a minus 5h. Plus 2 is just plus 2. And then I distributed this negative across this whole trinomial. So I'll have minus 2a squared plus 5a minus 2. And right away you start to see things cancel. This 2 and this 2 cancel. This plus 5a and this minus 5a cancel. And I still have my over h. It's just written out here as 1 over h times. It's easier than writing the big fraction, that's all. So I get limit h to 0, 1 over h times. Now I'm going to distribute this 2. I'll have 2a squared plus 4ah plus 2h squared. And then what's left over here? I've got minus 5h and minus 2a squared. The a squareds go. And we're left with these 3 terms. So now I'll go back and see if I can rewrite this as a fraction. I'll have my 4ah plus 2h squared minus 5h, and it's all being multiplied by 1 over h, or all being divided by h. Now we can factor an h from the top. And I'll have 4a plus 2h minus 5. And the h that I factor from the top can cancel with the h downstairs. So my limit is lim h to 0, 4a plus 2h minus 5. And as I send h to 0, 4a stays 4a, 2h becomes 2 times 0, which is 0, and minus 5 stays minus 5. So I get 4a minus 5. In summary, f primed of a is 4a minus 5. So if I asked you to find the slope of the tangent line at any x value, you would just plug that x value in here. Another way I could write this same thing, i.e. means that is, or is the same as, I could say f primed of x is 4x minus 5. Just changing the name of the variable. This looks more like we're used to thinking of functions. This is still defining a function, right? It's a linear function. You input the number a and it'll multiply by 4 and subtract 5. That's definitely a function. That's a rule that defines a function. And that function we call the derivative. So this is the derivative of the original function, which was 2x squared minus 5x plus 2. So this was the original function they gave us, and this is its derivative. In section 2.8, what we want to do is start making connections between the graph of this function and the graph of this function. Start making connections between the algebraic shape of this function and the algebraic shape of this function. And also to become more comfortable with the notation. First things first, questions on the computation. Questions on how I got to this line right here. Is all of this stuff feeling comfy? Having no yeses and no nos makes me nervous. Are we just still writing? Comfy cozy? Okay, good. Yeah, okay, good. All right, so my next move here is going to be to start observing some things. Here are some observations I would like to make about this function and its derivative. This is not a part of that homework problem. This is us breathing into section 2.8. Note, the original function, which is f of x, is quadratic. It's a polynomial of degree 2. And the derivative Hammy, be good, Bubba. Hey. Just because I'm teaching doesn't mean I won't come over there and take, yeah, don't do it. Don't do it, be good. Sorry. And the derivative, f primed of x, which is 4x minus 5, is a polynomial of degree 1. So quadratics, the cat is not in here. Sorry, if he wanders in, I've got 2 cats. If either of them wander in, I'll show them to you. But yeah, that's my dog, Hamlet, over there, who's licking his leg. All right, so let's come back here. The original function, quadratic. His derivative, linear. The degree goes down by 1. That's cool. Other important observations. Let's look at the graphs of these functions. All right, I can graph, well, is there anything else I want to show you about this? Degree 2. Let's look also at another algebra observation here. Yeah, no, we'll leave it at that. We'll leave it at that. And let's then say compare the graphs. So I'm going to use Desmos to help me out here. There's no harm in that. although we could figure out what the graph of this thing looks like by completing the square or by factoring it. I'm going to be lazy. There's no harm in a little bit of laziness when we're just discovering, playing around. On the one hand, I've got the original function, which is 2x squared minus 5x plus 2. And on the other hand, his derivative, I'm just going to put into Desmos as g of x because it doesn't understand the primed notation. We have this guy.
Oh, I mean, Desmos does understand it, but only if you put f prime of x without anything else. You just put f prime of x. But like without making it equal to anything. Like you wouldn't have to make it equal to anything.
Oh, no shit. Wow, nice observation. Okay. So the blue is the derivative, the red is the original. I'm going to sketch these on the notes, and I would like you to sketch them also. Thank you, Alexander, for that observation. Let's see, distance way over here. Something a little bit like this. So okay, so here's my original. This is 1, this is 2. And then my derivative I'll draw in here as a dotted line. Doesn't need to be perfect. My derivative looks something like this, yeah? So here is f of x, and here is f primed of x. Now think about the sort of questions that you were made to answer back in your algebra classes about increasing and decreasing, positive and negative. Let's ask and answer 2 questions about this guy. First, I'd like to find this x value here where the derivative crosses the x-axis. If I set this to 0 to find the x-intercept for the dotted graph, I'll find that that's 5 over 4. Right, so the x value right here, which is both the vertex for the original and the x-intercept for the derivative, is 5 over 4. Answer for me the following questions. Where is f of x decreasing? So f is the solid graph. Remember, where always means for what x values, always. And in case your pre-calc teacher did not drive this home enough, that is a universal. When you're talking about function behavior, and I ask you, where is something? I'm always asking for what input. So where, for what inputs, is the function f of x, this parabola, decreasing, going downhill?
From negative infinity to 1.
From negative infinity to where?
To 1.
Well, here's
5
1.
over 4.
Or 5 over 4, 5 over 4.
Yeah, all the way to the vertex. So from negative infinity to 5 over 4. And it's always open intervals, right? For increasing and decreasing. At this point right here, I am neither increasing nor decreasing. Where is f primed of x negative? So now I'm asking about the dotted graph. where, so for what inputs, for what x values is the dotted graph negative? So in other words, remember that means where is the graph below the x-axis? Or for what x values is the graph of the derivative, the dotted graph, below the x-axis? Is this stuff part of that? No, because the dotted graph is above the x-axis there. It's this stuff, which is from negative infinity all the way up to 5/4. Same answer as the previous question. Where is the original decreasing? Interesting, it turns out to be the same place where f primed is negative. Well, shit, that makes sense, because if f primed is negative, that means the slope of the tangent line is negative. If your tangent line has a negative slope, then you gotta be going downhill. Does this make sense? This tells us that f is decreasing means f primed is less than 0. And if we ask the similar questions about increasing and positive, where is f of x increasing? So for what x values is the parabola going uphill? Well, that's all this stuff. That's from 5/4 to plus infinity. And similarly, the answer to the question, where is f primed positive? That's where is this dotted graph above the x-axis? That's everywhere to the right of 5/4, which is again 5/4 to infinity. So this piece tells us something else, that f of x increasing means that f primed of x is greater than 0. Or f primed of x is positive, right? Being greater than 0 and being positive mean the same thing. So what this example illustrates is probably the most important connection you need to make in section 2.8. If the original function is decreasing, then the derivative will be negative there. If the original function is increasing, then the derivative will be positive there. And the other way is true also. If the derivative you know to be negative, then the original you can infer must have been decreasing. And if you know the derivative to be positive, then the original must be increasing. All of this, I'm definitely assuming that f is smooth, differentiable everywhere in its domain. There are pathological examples, but we want to get the basics understood. So I really want to take a second to make sure we all understand this. Questions, thoughts, comments, anything. Okay, I'm getting good answers in chat. Unfortunately, my chat notifications aren't working like they should, so I'm sorry if I end up being a little bit redundant. I see lots of good remarks there from Grayson, Sophia Harris, Andrew. Are there any questions about the connection between these things? Okay. Then what I'm going to do next, I'm going to draw a graph of a function without knowing anything about its algebra. I'm just going to draw a curve. And then we're going to try to come up with a graph of the derivative of that curve. And I'll walk you through the process, and I'm hoping that you guys will then be able to do this on your own. Because if you can do this, then you understand the derivative and you can answer all sorts of fun questions. So sketching f primed of x given the graph of f of x. We've actually done this once before, twice before even. We did this with the absolute value function, and then also in that homework problem that had the velocity, right? Where you were given the position graph and you had to come up with the velocity graph. So twice we've done this. Now we're going to do this in a little bit more generality. I'm going to make the function I use here as simple as possible. Let's do it like this. So we'll do something here like this, like this, this, like this, like this. All right, so I'm going to tell you this is the graph of f of x. Maybe over here I have -2, -1, 0, 1, and 2. And I want to try and come up with the graph of f primed. And again, I'm assuming that everything is nice and smooth and differentiable. We don't have any sharp corners or weird pathological behavior. Think of this as the graph of like a polynomial. I'm going to take a few points in here and I'm going to guess at the slope of the tangent line at each of those points. So over here, when x is -2, the slope of that tangent line, to me, this looks like maybe y equals negative x or something. The slope there looks like it's -1, maybe -1.5. Let's say the slope there is -1.5. The slope right here, what does the slope appear to be to you guys? Right at that bottom point, the slope of the tangent line right here.
0.
0, yeah. Here, is the slope there positive or negative?
Positive.
Definitely positive, and it looks to me to be about +1, right? This piece of the graph looks a lot like the line y equals x. So I'll say the slope there is like +1. Up here, the slope, again, looks like it's 0. And over here, the slope, kind of symmetric to this point, looks like it's a -1.5-ish. Each of these observations gives me a point on the graph of the derivative. So the points on the graph of f prime come from these slopes. When I say that the slope of the graph right here is about -1.5, that's saying that f primed of -2 is -1.5, i.e. the point -2, -1.5 is on the graph of f primed. right here, when I say that when x is equal to -1, the slope is 0, I'm saying f primed of -1 is 0. In other words, the point -1, 0 is on the graph of f primed. And same for these other points. So the next guy says f primed of 0, so the x value here is 0, is 1. So the point on the graph of f primed would be 0, 1. Here, I'm saying when x is equal to 1, the slope is 0. So f primed of 1 is 0. In other words, the point 1, 0 is on the graph of f primed. And then finally here I've got f primed of 2 should be about -1.5. So the point 2, -1.5 should be on the graph of f primed. If I want to get a decent sketch of the graph of f prime, I now plot these points. Try to analyze that curve. Let's do it. All right, so these are points on the graph of f primed of x. Start plotting these points. I'm going to take this up here in case anybody's still writing, but then down here I'm going to start plotting these points. So I'll give myself some coordinate axes. Okay, I'll mark this up here as 2. I'll mark this as 1. Mark this as -1, and down here as -2. Over here, we'll call this -1, call this -2, call this 1, and we'll call this 2, something like this, right? So this will be my graph of f primed. I know that the point -2, -1.5 should be on there. So that's like, I know the point -1, 0 should be on there. That's like here. I know the point 0, 1 should be on there, right here. I know the point 1, 0 should be on there. That's here. And I know the point -2, -1.5 should be on there. That's here. What does this look like to you guys? If you had to connect these points with a nice smooth curve, I think most of us would go for something like a parabola. Something like this. And we're sketching here. This isn't an exact science, because we're definitely just guessing at those slopes. But something like this is what f primed should look like. So I'm going to come back up here and set these two next to each other. What do you notice? Well, from -infinity to -1, the original function is decreasing. And from -infinity to -1, f prime is negative. Let's mute our mics unless we're saying something, por favor. Okay, so from -infinity to -1, the original function is clearly decreasing. And from -infinity to -1, f prime, the derivative, is below the x-axis. F primed is negative. And that makes sense. Look, everywhere over here, take any point over here, the slope of the tangent line is negative. So yeah, this graph, which is plotting those slopes as y values, will be negative. As we get closer and closer to -1 from the left, my slopes are negative, but they're getting closer and closer to 0, right? Right here, the slope is 0. Right here, the slope is negative, but it's not as negative as it was over here. And that corresponds with the idea of f primed getting closer and closer to 0. Here, f primed is still negative, but it's getting closer and closer to 0 because the slopes of the tangent lines over here are negative, but getting closer and closer to 0. Between -1 and 1, the original function f is increasing. Between -1 and 1, the derivative is positive. So positive derivative means increasing original. And increasing original tells you that the derivative is going to be positive. Over here, the derivative is positive, but it hasn't gotten as steep as it is here. Here, like right here, right at this point, just to the right of -1. That tangent line is positively sloped, but it's not as steep as it is over here. That's why this y value is positive, but not as positive as it is right here. And the pattern continues. As we get closer and closer to this horizontal tangent line, the values of my derivative should be positive because we're still increasing over here, but should be getting closer and closer to 0. Well, here that is. Positive, but getting closer and closer to 0. Here where the derivative is 0, I have my horizontal tangent line. And then the function starts decreasing, so the derivative becomes negative. I would like to hear your thoughts on this procedure for sketching the graph of f prime given the graph of f. Do we see where the points I started with came from here? At each x value, I guessed at the slope, that's all. And then I plotted that slope as a y value. Thoughts on this? Alyssa makes a good observation. Here, my original function had 2 turning points. So if this was a polynomial, the minimal degree is 3, right? 3 x-intercepts on the original, 2 turning points. So the minimal degree of the polynomial here is 3. This looks like a parabola whose minimal degree is 2. So yeah, the degree goes down by 1 when you differentiate a polynomial. Just like the example we looked at before where the original was degree 2 and the derivative was degree 1, here the original looks like it's degree 3 and the derivative looks like it's degree 2. So yeah, good observation. Yeah, if we differentiated again to look at f double prime, the derivative of the derivative, this guy's derivative would do what? Well, he would be negative everywhere over here, and he would be positive everywhere over here. What kind of thing does that? It goes from being negative to positive exactly once? That's got to be a linear function. So yeah, the derivative of this guy, the second derivative of the original, would be a linear function. What would be the, no, we'll leave it there. We'll leave it there. Other questions or comments? It is cool, right? Now here's the dope shit. You guys remember back in your pre-calculus classes where you had to find a min or a max and you would like circle it or you would write down the x value. But then in order to tell me the y value, you would need a perfect graph. You would need a graph where that point was like labeled or obvious or you could read it from a grid. Here, if I wanted to find the exact y value of this local max, I would find the x value where it occurs by setting the derivative equal to 0. And then I would take that x value and plug it back into the original here, and that would tell me the y value. So all sorts of those things that you used to have to guess at, or you used to have a graph to find, you used to have points labeled. Now you can find them if you can find the derivative. Okay. So let's grab another couple examples from section 2.8. We'll fiddle a little bit and see how you guys are feeling. So here they've done the same sort of thing that we've done, right? You look at the graph of the original, you estimate the slope at a few places, like these places they can say for sure the slope is 0. So those have to be x-intercepts for the derivative. Here we can say the slope, it looks like it's a little bigger than 1, a little smaller than 2, like 3/2. Okay, well that means the point here has to have y value 3/2 or 1.5 because that's the slope of the tangent line there. They've got a handful of calculations. We can go through these. I don't see any harm in doing that. There are more fun examples. They want to introduce other notations. We've already done this. Yeah, this will be fun. Higher derivatives, x cubed minus x squared. We can do that. But do we not have anything with vertical tangents? I guess we'll have to do that ourselves, huh? All right. So the graph I've given you here is actually very similar to the graph of x cubed minus x, but let's run through the algebra. So the exercise was this. Let f of x be x cubed minus x. Find f prime of x and compare the graphs. So f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h, right? Which is the limit as h goes to 0. F of x plus h is what I get by coming back here and replacing these x's by x plus h's. So that'll be x plus h cubed minus x plus h. This is f of x plus h, so I'll put it in some parens. And then I need to subtract from that good old-fashioned f of x, which is x cubed minus x. As always, if something is a singular object, we put it in parens, so f of x plus h gets its own parens, f of x gets its own parens. And then within f of x plus h, we need these little parens to make sure we're following our order of operations. Everybody comfy with why this limit looks the way it does and why I've used the parens where I have? Misuse of parentheses, one of those things that gets people in trouble in this class, so I'm just trying to be careful. To proceed from here, I'm going to need to FOIL out x plus h all cubed. I'm going to do that on the side. I'm going to do that down here. How can I do this without having other shit on the screen? We'll just say we're going to come down here, all right? So for you guys in your notes, just come off to the side somewhere. X plus h all cubed. If you know your binomial theorem, you can write this down quickly. If you don't know your binomial theorem, it will take longer. It's x plus h times x plus h times x plus h. You can FOIL the first two and then distribute the third across it. You will get x cubed plus 3x squared h plus 3xh squared plus h cubed. So this first piece, I'll have here lim h to 0 will be x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I have minus parentheses x plus h. That's minus x minus h. That's that first piece. From that, I need to subtract x cubed minus x. I'll write it like that just so we're not doing too much on one line. And all still divided by h. Again, I'll give a second for anybody who's still writing. In my next line, I'm going to just distribute this negative. So this will become negative, this will become positive. And I'm going to stop writing these parens here. Because there's nothing out front multiplying them, I can do that. If there was something out front multiplying them, I'd have to distribute it, but there isn't. So this is the same as lim h to 0, x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h minus x cubed plus x all over h. And we start looking for cancellation. I've got a minus x here and a plus x here, those go. I've got a minus x cubed here and a plus x cubed here, so those go. What's left? Three x squared h plus 3xh squared plus h cubed minus h. That's what's left. And if we factor in h from the numerator, I'll have h times 3x squared plus 3xh plus h squared minus 1. I can now cancel the h's, and I get lim h to 0, 3x squared plus 3xh plus h squared minus 1. And when I send h to 0, which I can now do because there is no longer an h in the denominator, I get this will go to 0, 3x times 0 is 0. This will go to 0, 0 squared is 0, 3x squared minus 1. Therefore, 3 dots arranged in a triangle like that stand for the word therefore. F primed of x is 3x squared minus 1. So this sort of derivative calculation, definitely something that's going to show up on exam 1. I will make you do something like this. Whether I'll make you FOIL out a degree 3 thing like this, it would be fair. But it would be a little bit tedious, but something like this where you have to calculate the function, the derivative of the function as this limit. I guarantee you it must show up on exam 1. It's one of the main things we've been practicing. We've written it so many different ways. So please practice this stuff, all right?
In the last line, how did you get rid of your h's?
I sent h to 0.
Okay.
Remember the whole thing here, we've got to limit h to 0 out front all this, right? So in this last step, my whole goal is to cancel the h from the bottom so I can plug in 0 for h. Once I get to this line, I don't have any h's in the bottom, so I can plug in 0 for h. And when I do that, this piece goes to 0 and this piece goes to 0. So it's all about this limit.
Thank you.
Mhm. Other questions? What else are we thinking? Yes, even if you know the easy way, you have to show me that you can do this. Right? It is a necessary skill. It's one of the main skills we're developing in Calc 1 is this algebra and this ability to analyze and understand what the limits mean. So even if you know the easy way, I will have a question on the test where you need to demonstrate this particular skill. So the exam, we talked about that a little bit at the start. The exam would have been next week had we not lost a little bit of time to the holiday. So the exam is going to be week after next, and the study guide will drop as soon as we've finished covering 3.2. Right now we're in 2.8. Okay. There were some earlier questions there. I see at 123, Grayson asked, can you take the derivative of a linear function? Yes, you can. And Alyssa's response there is good. The derivative of a linear function will be a constant function because the slope is constant. Right? So you can run through this process for a linear function, for sure. We've done it. And it will yield a constant. So the next thing they asked us to do is compare the graphs. So let me switch back to Desmos and we can take a look. F of x here was x cubed minus x. And the blue graph is the derivative. It's 3x squared minus 1. And you see the same sort of relationship that we talked about, right? This is x cubed minus x. This is 3x squared minus 1. If I add in the line, well, let's see. Where do we think this is? This is my horizontal tangent, right? Right here at this black point along the red graph, I have a horizontal tangent, and it definitely is occurring at the same x value as the x-intercept for the derivative, because the blue gives the slope of the tangent line for the red. So if I wanted to find this red point, which is approximated by Desmos as these decimals, if I wanted to find the exact x and y value there, what would we do? If I wanted to answer the question, where does f of x have horizontal tangent lines? Remember that question, where, always means for what x value. How would you answer this question? Given
Wouldn't you find out when 3x squared minus 1 equals 0?
Yeah, exactly. The slope of the tangent line. So question, answer. Slope of tangent line to f of x is f primed of x. Horizontal lines have slope 0. Thus, we solve the equation f primed of x equals 0. In other words, just as was said there, we need to set 3x squared minus 1 equal to 0. This is an easy quadratic to solve because it doesn't have any linear terms. That's the same as saying 3x squared equals 1, which is the same as saying x is plus or minus the square root of 1/3. So where does f have horizontal tangent lines? It has horizontal tangent lines when x is equal to plus or minus the square root of 1/3. I'm going to tuck this in here. Let's verify. I'm going to bring Desmos back up. So if you're writing, I'll give you just 1 second, but I'm about to bring it up. So get to a place where you can pause for a minute. Let's look at the line x equals negative square root 1/3. Boom, right here. All right, so red has a horizontal tangent line right here at the same place where blue is equal to 0. The other one, right there. Red has a horizontal tangent right where blue is equal to 0. These decimals are not 100% accurate, are they? The square root of 1/3 is an irrational number. It's not 0.5774. 0.5774 is a rational approximation to this. So when I ask you these sorts of questions, you need to give me exact answers. This is how I'll know you're not using Desmos to cheat. You give me exact answers, and I'll trust at least that you went through the computation. I'll need to see your work, of course. I know there are other ways to cheat. I'm pretty good at sniffing that stuff out, and I want to mention, just because there have been some exam questions asked, I am ruthless if I detect cheating. It's not something that I'm a nice guy about. So please, 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 just show me your own work and nothing else. All right, while we're here, you said you can tell me where f has horizontal tangent lines by figuring out where f primed is 0. Where is f of x increasing? How do we answer this? Well, we know f of x is increasing if the slope of the tangent line is positive. So f of x is increasing if the tangent line has positive slope. Oh, but the tangent line's slope is f primed. Thus, we need to solve. It's not an equation now. We need to solve the inequality. F primed of x is positive, is greater than 0. Okay, well that means 3x squared minus 1 is greater than 0. Who remembers how to solve this stuff? It's a little different than this. This will tell you where 3x squared minus 1 is equal to 0. And then if you have a graph, you can infer some things, but there's a procedure for this that you're supposed to have learned in pre-calc, solving nonlinear inequalities. Anybody remember?
I think I do. Just have to find the actual solutions to the equation, then you just check up for like in between and then the other two sides, right?
That's the idea. You factor the left-hand side. So I would start by writing this as x squared minus 1/3 with a 3 out front, which I can then force factor as a difference of squares. And you do the number line thing. So this is x minus the square root of 1/3 times x plus the square root of 1/3 is greater than 0. the solutions to the equation above are going to show up here as bits of these factors. And then you plot those on a number line for f primed. The numbers you plot here are the solutions to this equation from above. I call them important numbers for inequalities when we teach this in pre-calculus. In calculus, we call them critical numbers. The places where f primed changes sign are called critical numbers. So this guy tells me that this apparatus will be equal to 0 when x is negative square root of 1/3. And this guy tells me that f primed of x will be equal to 0 when it is equal, when x is the positive square root of 1/3. So those are the only places where f primed is capable of going from positive to negative. And remember, we're trying to figure out where is f primed positive. So that means everywhere in this region here, f primed is either positive or negative. Can't change sign anywhere except at these two places. So in each of these three regions, f primed is either positive and positive everywhere in that region, or negative and negative everywhere in that region. You can test a point from each of those regions. Like in here, between negative square root 1/3 and positive square root 1/3, I know 0 is in here. If I test x equals 0, that means I plug x equals 0 into the inequality, and you can do it in any one of these, they're all equivalent to each other. You'll find that this inequality is not true. F primed is not greater than 0 there, because if you plug in x equals 0, this is 0, and you get the inequality negative 1 is greater than 0. So f primed is negative in here. Because it's negative at 0, which lives in there, it's negative everywhere in there. And then because this is a parabola opening up, I know if it's negative in the middle, it's got to be positive everywhere out here. Or you could test a point from each of those three regions. So where is the original function f increasing? That would be anywhere f primed is positive. So f of x is increasing on the intervals negative infinity to negative square root 1/3. Unioned with positive square root 1/3 to infinity. And also, I can answer the question about decreasing. F of x is decreasing on the interval negative root 1/3 to positive root 1/3. No guessing, no looking at the graph required. We can answer these questions and answer them well. If you don't remember how to solve nonlinear inequalities like this, please visit the resources I posted for you in Canvas. Check it out, it's under the review material. Rational functions, extremes, logs, solving inequalities, right here.
Yeah, Mr. I have a question. I wanted to arrange some office hours to like discuss some questions. Thing is, they're not like explicitly Cog 1 though. They're like
I
just
remember,
random
yeah.
stuff.
So I haven't had time to reply to your email. We can talk about those in office hours this afternoon, but let's wait until people filter through and talk about the other things first. So I'll ask you to come by the office hour, but then just be patient while I deal with people who have questions pertaining to the class. So again,
Okay.
For those who are not remembering this process or didn't get a great treatment of this in pre-calc, please check out the following links in modules. There's one here for solving inequalities from Paul's online notes. He does lots of stuff like this. And then there's two down here, one for solving inequalities involving rational functions and one for solving inequalities involving polynomial functions. They both again link to Paul's online notes, and they've got lots and lots of examples where he writes everything out and then does this number line thing. And he's testing points. You can check these and use that to remind yourself how things go. Before I release you for the day, looking at this, because f primed is positive here, I know f is increasing there. Because f primed is negative here, I know f is decreasing there. Because f primed is positive here, I know f is increasing here. Just based on the number line, what must have happened at negative root 1/3? I went from increasing to decreasing. That means what happened here? If I go from increasing
There's
to
a curve.
decreasing, there's a curve. What
Or
specifically?
Slope was 0.
Yes, there's a horizontal tangent line. That's good, and we discovered that in the previous part, so that's a good observation. Think back to your pre-calculus class about extrema. Can you say whether any certain kind of extremum must have happened here?
Are those like maximum and minimums?
Perfect. If I go from increasing to decreasing, only one way to do that. You had to have rolled over the top of a hill, right? If I'm going uphill, 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 then downhill, 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 then that was the top of a hill. This tells me that this is a local max because I went from increasing to decreasing. What about this? I went from decreasing, decreasing, decreasing to increasing, increasing, increasing. What had to have happened there?
Local minimum.
Good. That's called the first derivative test. That's it. That is what the first derivative test is. It's a tool for finding mins and maxes. A min will be a place where you go from decreasing to increasing. Right here, I went from decreasing, because I'm decreasing everywhere here, to increasing, because I'm increasing everywhere here. That means this x value right here had to have been the location, the x value of a local min for the original function. And if you look back at our graph, right here is a local min, where I went from decreasing, decreasing, decreasing to increasing, increasing, increasing. And notice that that x value is also where f prime went from negative, negative, negative to positive, positive, positive. So solving the inequalities for f primed is how you figure out what's going on with f. Increasing, decreasing, mins, maxes, all that shit. Next time, we're going to talk about vertical tangent lines. I'm going to play this same game, but with a function that looks a little bit more like this. So what you'll notice here is that I do have a local min. I went from decreasing, decreasing, decreasing to increasing, 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 but it ain't smooth. It's pointy. And if I zoom way out, look at that graph of the blue function. He has a vertical asymptote at 0. So next time we're going to pick up the conversation here talking about vertical tangent lines. If you need more time on last week's homework, please submit an extension request. I've gone through a couple times today and cleared those. I'll be going through them one more time today. So please submit that extension request soon. A little bit later today, homework 4 will pop, and it's going to be all on this stuff. So comparing the graphs of f and f prime, guessing the graph of f prime from the graph of f, and finding things like mins, maxes, intervals of increase and decrease, all that good stuff. The other thing that you're going to see on the homework for this week is derivatives of power functions, polynomials, other power functions, and also exponential functions. So Wednesday is going to be split between these two topics, a little 2.8, little 3.132, and then Friday is going to be all 3.132. Please get the homework wrapped up before then, the homework from last week, that is. That way we can be putting all of our attention into this new material because this stuff is very important. Exam 1, again, is not likely to be next week. It's not going to be next week. We lost a day, and I don't want to rush this material. This material is so important. So exam 1 is going to get pushed a little bit. At the end of this week or at the beginning of next week, I'll release the study guide. And then you guys will have a full week to work on the study guide before the test. So exam 1, most likely not next Monday, but the Monday after that. All right. I'll talk a lot more about the exams, the precise procedures you need to follow and everything as we get a little bit closer. But I know a lot of people like to kind of think ahead. So that is the outline of where we are going. Please practice this stuff. Is there anything from the notes that you guys would like to have another look at to copy stuff down before we sign off for the day?
No, I'm good. Thank you.
Let me take one last look at the chat here because my notifications are not working. Okay, looks like pretty much everybody is happy. Alrighty then, so I'm going to go ahead and end the meeting here for today. Normal office hours today. You guys feel free to come by, talk about anything. If you want to come by or talk about things during another time, send me a Canvas message. Alex, if you wanted to talk about those fun problems that you had from your email, just come by the office hour today. And after I sort out everything else for folks who are worried about class stuff, we can talk about those. All right?
All right.
All right, I'll see you guys either in office hours or on Wednesday. Have a lovely afternoon.